Well, hello all. Today's topic comes from page 209 of Study and Master Grade 10, but Grade 11s and Grade 12s should try and do this as well. They should definitely watch this video because they also do electric circuits. So here we have a circuit and we've got some questions. Page 209, Study and Master Grade 10. Answering questions on circuits. In the circuit diagram below, the light bulbs. Ooh, we have light bulbs. How exciting, no resistors. At least this is slightly practical, although no one would ever wire a house like this with light bulbs in series and in parallel. But anyway, let's go with the flow. So the light bulbs all have the same resistance, same, and same. Switches S1 and S2 are open. Look, you can see the gap, they're open. Which bulbs, if any, will light up? Well, when you see an open circuit, can any current flow through? No current can flow through that circuit. No current can flow through that circuit. And our voltmeter is almost like having a... I just want to see if this is drawing. Oh yeah, it's turned into a pen. Okay, and our voltmeter is almost like a open circuit. So no current can go through your voltmeter. It's infinite resistance. So here goes the current, goes from the positive side. Let's draw it positive side. It goes, if we take conventional current, there's the direction of the current. It goes right through our ammeter, which has got no resistance, and it comes up to our voltmeter and can't get through there, can't get through there, can't get through there. So do you think that if the current can't get through any of these, that any of the bulbs will glow? Well, no current can get through it, so no bulbs will glow. Okay. B. I don't want to do all the answers for you, but I just want to help you here. Switch S1 is closed. Okay, so that one closes. And S2 are open. Which bulbs, if any, will light up? So now we went from having an open circuit to having a closed circuit. In other words, the current can go all the way from there, there, and that's where it can go. Another place it could go. Okay, so that's fine. So there, I just want to show you something. This has got 1, 2, 3, let's say of 1.5 each, 4.5 volts. Okay, so suppose this were a 4.5 volt battery. Notice that wherever you have no resistance, I'm just playing with this pen here, up to there the voltage is going to be the same, then it's going to go all the way there, it's going to hit a voltmeter. All of that, where I've colored it in blue, will be 4.5 volts. 5 volts. It's a very good habit to get into drawing your voltages. Okay, let's choose a color. I'm colorblind, so let's choose this yellow looking color here. Now everything there, I'm going to choose, okay, it doesn't seem to agree with that. Let's choose a red now. All there to there is also the same voltage. The moment it hits a resistor, the voltage change, and this would be 0 volts. So if this side, the blue, was 4.5, this side looks like red to me. I am colorblind, forgive me. It might be brown, it might be green, who knows. That is all one voltage as well. That's 0, that's 4. But wherever you see these other lines that are joined together with no resistance in between, let's choose another color. Okay, let's choose a kind of a yellowy color. Let's see if it'll draw it from here. I'm not great at that. There's a yellowy color or a greeny color, whatever color it is. There. That's also a different voltage. We don't know what the voltage of that color would be. And look, there's just one more line there that would be its own voltage. So we're looking at least 1, 2, 3, 4 different voltages in the circuit. So always get into the habit of looking for places where there is no resistance. In other words, where the wires are just joined, and all of those have the same voltage, and bring your crayons with you to the exam. Color them in like I've done. It'll make life so much easier. Okay, so switch 1 is closed and S2 is open. Compare the brightness of bulbs X, Y, and Z. Now, this is the only place where we have a closed circuit. So do you think those can glow? Yes, they can glow. They have equal resistance. So are they going to glow equally? Yes, equal resistance. Here's the only circuit that the current can flow in. And what determines how brightly they glow? And that is the power. Oh, that's not a very good color. Let's delete that. Let's try a different color. Let's get a blackish color. Okay. The power is going to be equal to volts times amps. Okay. So the brightness of the bulb depends on the power. So the brightness, let's put a B there for brightness, will equal the power, and the power will be equal to the volts and amps. So the same current flows through both of them. Now the other question is, does the same voltage apply to both of them? Now look, we can ignore that circuit because it's an open circuit. We can ignore that circuit because it's an open circuit with a voltmeter. The voltmeter acts like an open circuit. It's almost like you could say you've got an open circuit here. It's the same as that. No current can flow through a voltmeter because it's got infinite resistance. Okay, so now look at this. You've got two resistors in series. And what do we say that resistors in series are? Resistors in series are voltage dividers. If this was 4,5 volt, which it doesn't say it is, and don't pretend that it is, I'm just saying, let's suppose it is. It doesn't matter. It could be 6 volts, it could be 4 volts, whatever. It's going to divide the 4,5 equally between the two because they equal resistance. How do resistors in series divide the voltage? Depending on their resistance. The bigger the resistance, the bigger the voltage division. So each will get 2.25 volt drop across them if this was 4.5. So it's got the same voltage, and as you should know by now, if you've got two things, anything in series has the same current. So these bulbs got the same voltage, the same current, both of them glow equally brightly. That one, open circuit, doesn't glow at all. See how easy that was? Okay, now switches S1 and S2 are closed. Compare the potential difference across the bulbs X, Y, and Z. This is why you grade 11s and 10s must watch this video. Okay, so let's close the circuit. Okay, close the circuit. Now current can flow through. From there, it can flow also through there, and then it can flow through this bulb as well, now that the circuit is closed. Okay, but now here's the question. This now becomes the same blue, so there's the same voltage there and there. Because this is all one conductor, I guess I could go, I don't remember which blue it was, and just say it was that blue. This we could just say is this is all now the same blue. So it's all got the same voltage there. Okay, so now what is the brightness going to be? Look, this is actually quite a tricky question, what the brightness. Switches are closed, compare the potential difference. Okay, they just want to know what's the voltage. I know immediately when you've got two resistors in parallel, you always get less resistance than having one resistor. And if you have 3 or 4 resistors in parallel, you get even less resistance. What we call the total resistance of the resistors in parallel becomes less. So I'm trying to think of the word that they use for the combined resistances of resistances, the effective resistance or the equivalent resistance. Yeah, So these two resistors are going to be less. You could work it out. Say each of these was 1 ohm and 1 ohm. So what is the formula for resistors in parallel? My little ball here is doing resistors in parallel. We use the formula 1 upon resistors in parallel equals, this is terrible. Let's suppose each of them was 1 ohm. 1 upon 1 plus, come on, plus 1 upon 1. Okay, so to be, there, it's come back to me, plus 1 upon, plus 1, no, it's grabbing something, it wants to move it, 1 upon 1. I'm not having great joy. Okay, so what's 1 upon 1 plus 1 upon 1? It's 1 plus 1 is 2. So 2 inverted is 1 upon 2, and so the total resistance would be 1 half of, so half an ohm. So our total resistance would now go to being half an ohm. So this went from, if we had just 1 there, from 1 ohm to the total resistance of both of those, if each was 1 ohm, would be now half an ohm. It's gone to half the resistance. So now we've got half an ohm is the effective or equivalent resistance, and 1 ohm. So where's the voltage going to drop? It's going to drop mostly across here, and half of what it drops across here, it'll drop across there, because this is half the resistance. Resistors in series are voltage dividers. This is now all, you could consider all of those two is just one equivalent resistor of half an ohm. So we've got half an ohm and 1 ohm, so the voltage is going to drop, if you divide it 4.5 by 3, which comes to 1, it's going to drop 3 volts here and 1.5 volts there. If this were 4.5, but we don't say that it is 4.5, but it would drop 2/3 of 4.5 and 1/3 over here, because this is twice as big as that. Okay, so that's the potential difference. When switches S1 and S2 are closed, the readings on the ammeter is 0.5 amps. Okay, this is the first time they actually give us a reading, so we have to ignore, we can't say this, I was just using this as an example. It probably isn't 4.5, so I'm just cancelling that out in my mind. The only thing I know is that that ammeter reading is half an amp. What would be the currents through X and Z? Okay, so there's X and Z. What would be the currents through X and Z? Well, X and Z are, watch what happens to the current. The current comes here, comes here, splits up, goes through X, goes through Y, the currents come back together, and then they go through Z. So you're getting half the current through X, half the current through Y, so the current in Z would be twice as much. What would be the currents through X and Z? X would be half of Z. Another bulb is connecting in parallel to X and Y. Will the reading on the ammeter increase? Well, let's suppose that this was a bulb. Let's just turn that into a bulb instead of a voltmeter. So now we've got 1, 2, 3 bulbs, and they're in parallel, because it says here another bulb is connected in parallel to X and Y. There's X, Y, and there's a third bulb. Well, what did we say? The more bulbs you have, the greater the current, so the current is going to increase. Will the readings on the ammeter increase? Yes. Explain your answer. Because this is decreasing the resistance, and what's the relationship according to Ohm's law? The less the resistance, the more the current, Ohm's law. That's how I'd explain it. Okay, now number 2. Consider the circuit diagram below and answer the questions that follow. Phew, glad to get rid of that mess. Look at that mess. It looks like my 2-year-old kid got hold of it. Luckily I don't have a 2-year-old kid anymore. It was lovely having one, but that was many, many decades ago. Consider the circuit diagram below and answer the question that, and thank the good Lord I don't have any grandkids. No 2-year-olds. Okay, but I digress. Consider the circuit diagram below and answer the questions that follow. Ooh, what have we got here? We've got a voltmeter. We've got 2 cells, yeah. We've got a 1 ohm resistor, an ammeter. Oh, that's a 10 ohm. Is that 10 ohms? You know, I'm just going to have to get my glasses. It's an ohm or a 10. Those are ohms. 1 ohm, 1 ohm, 1 ohm. Okay. So we've got 1 ohm, 1 ohm, and 1 ohm here. Consider the circuit diagram below and answer the questions that follow. What are the readings on ammeter A2 and A3? And that's 3 volts. That's 2 amps. 3 volts, 2 amps. Okie doke. And what are the readings on ammeter A2 and A3? Well, there's A1. There's that's voltmeter 2. There's, let's put my glasses on. Oh, there's A2. Okay, so that's in series. So if that's 2 amps, what do you think that is? The same current that comes out of here goes through there. If it was 2 amps there, it's 2 amps there. Then it comes and splits and goes through each of the 1 ohm resistors. And then the current can't go through a voltmeter. Okay, so what are the readings on A2 and A3? Both 2 amps. Calculate the equivalent resistance of the circuit. Ooh. So we've got to add 2 of 1 ohm each in parallel. Remember from the previous problem, we luckily chose 1 ohm, so we know that that's a half, and that's 1. So what's the equivalent resistance of the whole circuit? It's 1.5. Those 2 are in parallel, so they come to a total of a half an ohm, and that added to this is in series with those 2, comes to 1.5. Calculate the equivalent resistance, predict the voltmeter reading on V2. Okay, where is V2 here? There's V2. Okie doke. So, what do we have? We have, the whole thing is 3 volts. This is 1 ohm. These together are half an ohm. So we know that this 1 plus the half is going to be split because resistors in series, because you can consider this all as 1 resistor in series with this one. So our total resistance is 1.5. And in that 1.5, it's going to drop it 3 volts. So every half is going to drop it 1. Think about it. If your total resistance of the circuit is 1.5, 1.5, then the 1.5 drops over 3. So each resistor, so we've got a half, and 2 halves makes 3 halves. And the 3 halves are going to drop at 3 volts. So I know that this voltmeter, because this is only a half, it's going to get half the voltage of that one. So if there was a voltmeter, I know across this one, if there was a voltmeter there, it would have to be twice the voltage of that one. So this one I'm saying is going to be 1 volt, and that's going to measure 2 volts. And that's going to be 2 plus 1, 3 volts. I'm just working it out by sheer logic here. Half the resistance, half the voltage. And we're dividing 3 by a total of the 1.5 ohms is going to share the voltage. Predict the voltmeter reading on voltmeter V2. We've done that. Oh, okay. So we've done the problem. Great. An electric light bulb is connected to the 230 volts main supply. Calculate the amount of charge that flows through the bulb in 1 hour if the current through the bulb is 0.5 amps. So charge, it'll be on your data sheet, is equal to amps times time. And time, don't forget, is measured in seconds. So you could work out how much charge, you got your amps, how many seconds in an hour, work it out, the seconds an hour times the current will give you your charge. What will happen to the resistance of the filament after the light bulb has burned for an hour? Well, where's the filament of the light bulb? Oh, this is just a theoretical light bulb. Okay. So it's just a light bulb. Okay, as it gets hotter, the resistance increases. So what will happen to the resistance? It increases. The hotter something is, the more resistance it's got. Calculate the equivalent resistance of these circuits. Oh, look, you got 6 plus 3 plus 12 in series. What do? You just add them. 6 and 3 is 9 plus 12 is 21, isn't it? Okay. Then those two, you know the formula for in parallel. You add the two in parallel. Don't forget to invert. You add that one because those two are now equal to one resistor. 1 upon 3 plus 1 upon 12. Type it into your calculator. You invert it by saying 1 upon your answer. Add that to that, you get your answer. And then you got 1 upon 6 plus 1 upon 3 plus 1 upon 12. And you add them on your calculator, then don't forget to invert it 1 upon your answer, and then you will find the equivalent resistance for all those circuits. Well, that was painless enough. I thought that would be difficult, but okay. Now we're going to give you a Google quiz on this. Ha!